Welcome to lecture 23, where we see short expansions of elementary functions. These short expansions represent a link between limits and infinitesimals. Now, I'll first list a number of expansions and provide the proof for these expansions, and then we'll see how to apply these expansions to solve problems. First expansion will be the expansion of sine of x, and we say that sine of x can be expanded into x plus little o of x. Now I will be assuming for each of these expansion then that x will tend to 0. Okay, so let me give the proof of this. I want to prove that sine of x can be expanded into x plus little o of x, which is just like saying that sine of x minus x is equal to little o of x. Now we can rewrite sine of x minus x, and well, we can divide by x and multiply by x, right? So this becomes now sine of x divided by x minus 1, all this multiplied by x, and we immediately recognize this to be our g of x and this to be our omega. So we need now to prove that the limit as x goes to 0 of sine of x divided by x minus 1 is equal to 0, which is obvious since this is a fundamental limit that will tend to 1. Okay, so first expansion proved. Second expansion. Tangent of x can be expanded into x plus little o of x. Again, we can rewrite this as tangent of x minus x equal to little o of x, and this can be also rewritten as tangent of x minus x divided by x and then multiplied by x, which is tangent of x divided by x minus 1, all this times x. And we recognize once again that this is g and this is omega. So we are now led to the limit x goes to 0 of tangent of x divided by x minus 1. But we know that this is 0 because this is another fundamental limit that will tend to 1. Okay, so this is another expansion proved. Third expansion. Arctangent of x can be expanded into x plus little o of x. Usual procedure, arctangent of x minus x equal to little o of x. Dividing and multiply by x, we have arctangent of x minus x divided by x times x, which is arctangent of x divided by x minus 1, all multiplied by x. This is our g, this is our omega. So we need now to prove that the limit as x goes to 0 of arctangent of x divided by x minus 1 is equal to 0. But we know this because this is a fundamental limit. Okay? Fourth expansion. Arc sine of x equal to x plus little o of x. This is a totally similar limit. Let's do this for exercise. Arc sine of x minus x little o of x, arc sine of x divided by x minus 1 times x. So we have our g here, and we see immediately that this omega tends to 0. So this is already another expansion proved. More interesting is this expansion 5. We want to expand logarithm of 1 plus x into x plus little o of x. Remember that all these are valid for x that goes to 0. Okay, so this is just like saying that the logarithm of 1 plus x minus x is equal to little o of x, which in turn means, by usual process, logarithm of 1 plus x minus x divided by x and multiplied by x. This is logarithm of 1 plus x divided by x minus 1 times x. So once again, we recognize our g here and this omega that clearly, because of the fundamental limits, will tend to 0. Expansion 6. E to the x equal to 1 plus x plus little o of x. Let's prove this, which is just like saying e to the x minus 1 minus x equal to little o of x. E to the x minus 1 minus x divided by x multiplied by x. This is e to the x minus 1 divided by x minus 1, all this times x. So this is g and this is omega that tends to 0. Okay? Right, so let's continue our list of expansions with the expansion number 7. Cosine of x is equal to 1 plus little o of x. Okay, let's prove this, which is just like proving that cosine of x minus 1 should be equal to little o of x. And again, dividing by x squared and multiplying by x squared, we get cosine of x minus 1 divided by x squared times x squared, which we can rewrite as x times x. Well, we recognize now that this is g, right? And instead all this is omega. But it is easy to see now that the limit as x goes to 0 of cosine of x minus 1 divided by x squared times x, well, we see that this is one of the fundamental limits. This is converging to minus 1/2. This goes to 0, so this limit is indeed 0. Now, cosine of x can also be expanded in a different way, and this is the second expansion that we are doing, which is the following. Cosine of x can be expanded into 1 minus x squared divided by 2 plus little o of x squared. Okay, so let's prove. So we see that in the expansion now we are having a second term. So this is the first time that we see a second term of the expansion. And this of course is just let's say, an anticipation of what we will see in one of the later lectures when we will have long expansion for the function. We may have 2, 3, 4, infinite many terms in the expansion. Okay, but for the time being, let's prove this expansion. Okay, so what we want to prove is that the cosine of x minus 1 plus x squared divided by 2 is equal to little o of x squared, right? Okay, so now we can rewrite this by, as always, dividing and multiply by x squared. So we have cosine of x minus 1 divided by x squared plus 1/2, all this multiplied by x squared. And we recognize that this is g and this is omega. So we need now to check that the limit as x goes to 0 of cosine of x minus 1 divided by x squared plus 1/2 is indeed equal to 0. But we know this because this, by the fundamental limits, is just minus 1/2. So also this other expansion of cosine of x has been proved. Now, if we consider this result, we could possibly use this result. So this result can also be used to prove the expansion 7. And let me explain how. Remember that the expansion 7 was that cosine of x minus 1 was equal to little o of x, right? So, but now we want to rewrite this as follows. Cosine of x minus 1, okay, and if I add and subtract x squared divided by 2, right? So what we get now is basically that because of the expansion number 8, we can replace cosine of x minus 1 plus x squared divided by 2 with o of x squared minus x squared divided by 2, right? And now we know that if it is o of x squared, we proved that this is small o of x, but also x squared divided by 2 is small o of x. So we have 2 times, we have little o of x plus little o of x, which once again is little o of x. This is one of the algebraic properties of the little o. So we have now a number of expansions. Let's see how we can apply this. So let's apply these expansions to the computation of some limit. So let me start with this example. Let's say we want to evaluate the limit as x goes to 0 of this fraction. Tangent of 3x plus e to the 2x minus 1 divided by the arc tangent of x plus sine of 3x, right? So, and I can immediately say that this limit is 5 divided by 4. Okay, how can I do this? I will explain now. Now, we can follow 2 possible routes, okay, for the solution. Now, first approach is basically the classical, by just using fundamental limits. So if we do this, what we get is limit as x goes to 0. Now let me re-express the fraction by just using the fundamental limits. We immediately realize that the tangent of 3x, if we divide by 3x and multiply by 3x, well, we see that for x that goes to 0, this clearly is something that will go to 1. Okay, so first element has been fixed. Then we have e to the 2x minus 1, that if we divide by 2x and multiply by 2x, we have another part, another fundamental limits that will tend to 1. Good. So let's go to the denominator now, and we have arc tangent of x. Again, we multiply by x and divide by x, and we have these other fundamental limits that will go to 1, and then we have plus sine of 3x, which we can divide by 3x and multiply by 3x. So once again, we have that these will go to 1. So this limit is simply the limit as x goes to 0 of 5x divided by 4x, and by simplifying the x's, we have 5 divided by 4. Okay, so this will confirm the initial intuition. Now the idea is that how was I able to immediately realize that this limit was 5 divided by 4? Because I knew that from the first term, tangent of 3x, I will get 3x. From the second, I will get 2x. From this, I will get an x. From this, I will get 3x. So this will easily lead me to the conclusion that by simplifying all x's, I have 5 divided by 4. But let's now use the small expansion, okay, which are basically using the little o to solve the limit. Okay, so what I'll do now is just replacing each of the function with their corresponding small expansion. So tangent of 3x will become 3x plus little o of 3x, and by the algebraic property of a little o, we know that this is simply 3x plus o of x. E to the 2x minus 1, well, this is 2x plus little o of 2x, which is 2x plus little o of x. Then we have arc tangent of x, which is simply x plus little o of x. And then we have sine of 3x, which is 3x plus little o of 3x, which is 3x plus little o of x. Okay, now we are ready to replace the function with their corresponding expansion, and what we get is, well, tangent of 3x becomes 3x plus little o of x. E to the 2x minus 1 becomes 2x plus little o. It is useful to consider that in general, this might be useful in future. In general, if we have the limit as x goes to 0 of some small o of x to the k, divided by x to the k, well, of course this is equal to 0. What is the proof of this? Well, this is because clearly if we have small o of x to the k, well, this is something that can be written as omega of x times x to the k for omega of x that goes to 0. So clearly the fraction o to the x to the k divided by x to the k, if we replace with omega times x to the k, this will simply give omega of x that of course will tend to 0. So this proves the statement. Okay, so let's solve another limit now. Example 2. Limit as x goes to 0 of sine of 3x plus arc tangent of x squared divided by logarithm of 1 plus 7x plus sine square of x. And we recognize now that this limit is simply 3 over 7. And I will explain why this is the case. But let's now just proceed with the substitution given by the expansions. Okay, so we start with the sine of 3x, which we know at this point is just 3x plus little o of x, and arctangent of x squared, well, this is x squared plus a little o of x squared, which we know is simply little o of x, because x squared is little o of x, and of course o of x squared is little o of x. At the denominator we have logarithm of 1 plus 7x, which is 7x plus little o of x, and then we have sine square of x. Now this, we know that sine of x is x plus little o of x, so we need to take the square of this, but the square of this is x squared plus 2 times x times little o of x plus o of x, all this to the square. And now we see that x to the square is simply little o of x, right? Then we have that also this product x times little o of x is another little o of x, and also ox to the square is another little o of x. So we can conclude that this is finally little o of x. And now if we go and replace these expansions at the numerator, we sine of 3x will leave 3x plus little o of x. Arctangent of x squared again is going to give me little o of x. The logarithm will give 7x plus little o of x, and sine squared will leave me with little o of x. And clearly this is just writing 3x plus little o of x divided by 7x plus little o of x. And clearly we know by the same process, we know that this will converge to 3.7. So we are also for composition assuming that x tends to 0. Okay. First example of a composition is e to the sine of x. Now clearly this is just a composition of two functions. Okay, so composition of e to the x n sine of x. What are we going to use for this? Well, we will be using the expansion of e of x. We know that e of x, e raised to the x, it can be expanded in 1 plus x plus little o of x, right? And then when writing the composition e to the sine of x, well, this will become 1 plus sine of x plus little o of sine of x. Now, regarding this sine of x, we can say something on this. Let me explain how we can evaluate little o of sine of x. Now, little o of sine of x, right, is a function, is a little o of sine of x. That means that this can be expressed as some omega of x times sine of x, right? Good. But now we can also rewrite this as follows. We can rewrite as omega of x times sine of x divided by x, all this multiplied by x, and we realize that this is another omega 1 of x that clearly tends to 0, because sine of x divided by x is a fundamental limit that will tend to 1. Omega of x tends to 0, so the product omega 1 will tend to 0. So we can conclude finally that o of sine of x is little o of x, and we will be using this now, because now we will be writing 1 plus, well, we are now reusing the expansion of sine of x, and this will become x plus little o of x, and for little o of sine of x, we'll just replace little o of x. So this will leave us with 1 plus x plus little o of x. Okay, so this will be the expansion of e raised to the sine of x. Now, an alternative way, so in alternative, we can do the following. We can write e to the sine of x. We can just replace the expansion of sine of x. So we have e raised to the x plus little o of x, which is e to the x times e to the little o of x, right? And now we replace e to the x with 1 plus x plus little o of x. So this is basically the expansion of e to the x. And then we need to replace e raised to the little o of x with, of course, 1 plus little o of x plus little o of x, right? Let's proceed now and develop the multiplication. Well, but before that, we can just simplify, okay, the second part. So we can leave this as it is, 1 plus x plus little o of x. And for the second factor, we can write 1 plus simply little o of x, because we know that, right? So we know that this little o of x can be easily proved to be little o of x. Okay, so this will leave us with the simplified second factor. Okay, now let's proceed with the multiplication. What we have is that 1 plus little o of x. Now we want to make use of this composition result when solving a limit which is a little bit more involved. Okay, so let me give this other example. Let's pick this limit as x tends to 0 of this fraction. We have e raised to the sine of x plus the logarithm of 1 plus arctangent of 2x minus the cosine of 7x. And then we have arc sine of x to the square plus 3 times tangent of 5x. Okay, so we want to see what this limit will bring. And by just looking at this, we can basically immediately realize that this limit is 1 over 5. Okay, I'll come back on this intuition later, but let me first apply all the expansions for every function. Okay, so let me start with the e raised to the sine of x. Okay, we just proved that this is equal to 1 plus x plus little o of x. Then we have cosine of 7x, which is equal to 1 plus little o of x. Okay, we have now just used the first expansion of the cosine. Well, we can prove this if we are not convinced. Okay, the first expansion would be 1 plus little o of 7x, but by the properties, okay, of little o, we know that this is just like saying 1 plus little o of x, and this proves the expansion. Then we need to expand the arc sine of x squared. Okay, and I'm saying that this is just equal to little o of x. Now, why is that? Let me prove this other expansion, because actually arc sine of x squared would be equal to x squared plus little o of x squared, but both of these are equal to little o of x, so this proves the expansion. Then we have at the denominator the logarithm of 1 plus the arc tangent of 2x. Okay, and well, this can be expanded in 2 steps. Okay, let me do the first expansion by just using the logarithm of 1 plus something that goes to 0. Okay, so this will become arctangent of 2x plus the little o of arctangent of 2x, right? We know that. But now we do another expansion for arctangent of 2x, and we get 2x plus little o of x. And for the second, of course, we have little o of 2x plus little o of x, which basically is little o of 2x. Okay, and this, again, reapplying the usual properties, we get simply 2x plus little o of x. So this will be the expansion for the logarithm. Okay. Finally, we need to expand the tangent of 5x, and we can immediately say that this is 5x plus little o of x. Okay, so we are ready now for the replacement. Okay, so remember that we had what? Well, we had, first thing is e raised to the sine of x, which becomes 1 plus x plus little o of x. Then we have logarithm, but the logarithm is 2x plus little o of x. And then we have minus cosine of 7x, which implies simply minus 1. Well, there would be minus little o of x, but we know that this is just like saying little o of x. And at the denominator we have the arcsine, which gives little o of x, plus we have what? We have 3 times tangent of 5x, which simply is 15x plus another little o of x. Okay, and we can cancel the two ones, right? And this finally gives, if we sum all the x's, we get 3x on top plus little o of x, and then we have 5x below plus little o of x, and this clearly converge to 3 divided by 15, which is nothing else than 1 divided by 5. So how could I had an intuition regarding this? Because from the first look at the function, I see that clearly at the denominator what really counts is only this, because the arcsine of x to the square will go faster to 0, so this can be neglected. Okay, and instead what I have the numerator is